Hey y'all, I'm Ivey.
I'm Gibson.
I'm Meg. I'm Clary.
And I'm Carlisle.
And our thesis presentation is about our exploration into an animal model of adolescent binge drinking. So to start off, let's talk about adolescence. Adolescence is a period of early life in which the brain is continuously maturing. This is a period in time that's characterized by high risk-taking, thrill, novelty, and sensation-seeking, and needs for social interaction, social acceptance, and exploration. This is also a period in time in which the brain is highly plastic. Plastic simply refers to the brain's ability to change, and it also has a lot of experience-dependent plasticity, which just refers to the fact that your experiences change how your brain matures. Binge drinking is a common form of alcohol consumption in human adolescents. Adolescents tend to drink around 2 to 3 times more alcohol per drinking instance as compared to adult counterparts, and there's been a correlation drawn between binge drinking and continued impulsivity. See, impulsivity typically decreases throughout adolescence, but in heavy binge drinkers that do it throughout adolescence, not so much. And although heavily mediated by environmental and genetic factors, it has also been found that binge drinking plays a significant role in the development of alcohol use disorder. Binge drinking also endangers brain development. The prefrontal cortex is the last structure in the brain to develop. It finishes cooking around age 25, which makes it of particular interest to this field of study. And early alcohol exposure and binge drinking typically causes deficits such as increased impulsivity and increased risk-taking. Another thing that's severely impaired by, or has shown to be significantly impaired by alcohol exposure in adolescence is behavioral flexibility. Behavioral flexibility is the ability to change one's behavior based on environmental cues and to change rules and parameters based on what's given to you. Deficits in that would be called behavioral inflexibility or habitual responding, and it would manifest as not being able to alter one's response to a stimulus even though that response is no longer garnering a reward or reinforcing technique. AIE stands for adolescent intermittent ethanol exposure, and it tends to disrupt frontal cortex and increases that behavioral inflexibility. AIE tends to affect performance in operant tasks in rodent studies, and in terms of research methods, forced exposure seems to garner these deficits, but we don't really want forced exposure to alcohol to garner these deficits in rodents. We want voluntary exposure to garner these deficits because it's a more accurate model of human alcohol consumption. So we've set out to create a novel animal model of adolescent ethanol exposure to try and replicate human patterns of alcohol consumption and further addiction-like behaviors. Our hypotheses in the following study were that 1, we would expect that alcohol consumption would be high initially and decrease as time went on, just based on the background literature. The second hypothesis was that subjects who were exposed to alcohol in general would perform worse on task phases than controls, and that those in the chronic group, or those getting alcohol every single day, would perform worse on tasks compared to the acute group, or those getting alcohol every other day, and their control group. And then our fourth and final hypothesis was that increased alcohol consumption and higher ethanol preferences would correlate with worse performances on task phases.
Our participants for this study included 24 male Sprague Dawley rats that we got on postnatal day 21. They were given about a week to adjust to their new environment before alcohol access began on postnatal day 28. They were separated into 3 groups: the control group, which was given a 2-bottle choice between tap water and distilled water; the acute alcohol group, which was given the 2-bottle choice between tap water and a 20% ethanol mixture; and the chronic alcohol group, which was given the 2-bottle choice between tap water and our 0.2% saccharin ethanol mixture. They were given every other day access to alcohol, except for the chronic group, which was given access to alcohol every day. Rats were tested in a standard scanner operant box that contained 2 levers, 2 cue lights, and a red light at the back of the chamber to illuminate it. The experiment started with adolescent intermittent ethanol exposure, which was a 5-week period of alcohol access from postnatal days 28 to 61, followed by a deprivation period, which was 2 weeks of no alcohol access. From here, the rats went on to their behavioral training, in which they started off with lever training, where they learned to associate a lever press with a sucrose pellet reward, followed by acquisition, in which a cue light above one of the levers would signify which lever was the correct response, consistent with their side preference established in lever training. From there, they went to set shift, in which they would ignore the light and press the other lever that was opposite their side preference. Then followed reversal 1, in which it followed the same paradigm as acquisition, in which the cue light indicated the correct response, consistent with their side preference, followed by reversal 2, which followed the same paradigm as set shift, in which they would ignore the cue light and press the other lever that was against their side preference established in lever training.
Moving on to results. Here we have a couple graphs themed around the consumption of ethanol throughout our study. Up top, these two represent average ethanol consumed between the first couple sessions and the last couple sessions across all three groups. We see a decrease in amount consumed across groups. We see a significant decrease between our chronic saccharin in the first and last couple sessions. For that graph, over on the far end for me, we have the amount consumed across all sessions averaged together for our acute group and chronic group. We see a significant difference in the amount consumed with the chronic obviously drinking much larger. Down on the bottom here, we move away from amount consumed and we move towards preference. So here we see that for the first couple sessions and the last couple sessions, the acute group had a significantly stronger preference for ethanol compared to the chronic group. For training, moving into our behavioral sections. For lever training, we unfortunately saw no significant differences, but we do see that the chronic group took a little bit more time to reach criteria compared to the other two groups. Moving over to the acquisition of the cue light, we see that the acute group took a little bit longer than the other groups. Again, no significant differences. For set shift, we see that in terms of time to criteria, the acute group took a little bit less time to reach criteria compared to the other groups. Not significant, unfortunately. In terms of percent correct, we see that the acute group performed a little bit worse than the other groups. Again, not significant. For all groups, we saw an increase in time to criteria when they had to switch to the side cue, and we saw a decrease in percent correct for the same. For our reversals, both of these are 4% correct. Over here we have reversal 1. We see all three groups essentially the same for the reacquisition. All groups see a decrease in percent correct for the actual reversal period, and if you can see it, the acute and chronic groups are ever so slightly lower than the control groups in terms of percent correct, and we essentially saw that repeated for the second reversal over across from me.
Okay, so basically the goal of the study was to create a voluntary consumption model that closely related or mimicked human drinking patterns. So while a forced model often gives more behavioral deficits, like I said, we wanted to create a model that would represent more of human-like patterns. So Rodinich and colleagues conducted a study that used a forced exposure model. So their mice were given 5 liters of alcohol per minute through vapor inhalation, and our rats were given 750 milliliters of ethanol on their allotted exposure days. So as you can see, the Rodinich study gave much more alcohol to their mice than we did to our rats. So they did see behavioral deficits. So this could lead to an explanation for why we did not see as many significant behavioral deficits in our rats.
Okay, so we had a couple of limitations. First of all, we didn't do any baseline testing. So if there were behavioral deficits in the rats prior to exposure to alcohol, those were unknown to us. We also did not look into alcohol consumption during adulthood, so we do not know the long-term effects of alcohol exposure to alcohol, or adolescent, exposure to alcohol. And then finally, we only tested on male rats. So these results may not generalize to female rats. Several studies have demonstrated that sex differences and the effects of adolescent ethanol exposure on subsequent ethanol intake and the outcomes found in males do not necessarily generalize over to females. Therefore, future studies should include both males and females. A future direction for these rats in particular is that they will be inserted with a catheter to allow for cocaine infusion to look at the effects of alcohol exposure during adolescence as a gateway towards other substances like cocaine in adulthood, which goes back to the risk-taking behavior that can evolve from exposure to alcohol during adolescence. And then we would like to thank our advisor, Dr. Carr, for her guidance and support during our research, and thank you all for listening.